Okay, hello. Well, to make a long story short, I could go just to my conclusion page because everything has been said. And so this is actually very much in the line of all the colleagues. This is maybe also why we found each other, that we know, of course, that there are all these problems. We have solutions partially, but we are not there yet. So I still give you some information. First, some words about my group. We are in Kiel in Germany, and I've been working in 3D for over now, I guess, 25 years. So, and I'm still not finished there. I've been working in all the EU projects, actually the frameworks from 3 to 7 to Horizon 2020. So I'm really looking forward to all the collaborations. And where is here? Okay, so the goals that I want to talk about is, of course, 3D computer vision for 3D scene analysis, and there are some important notices like how to handle this, make it fast, make it really 3D, how can you apply it, and we have seen a lot of examples in the previous talks. This is some older work. If, for example, you have some 3D scene rendering from what we call structure for motion, you can do a reconstruction of such a scene. That was actually from a European project. You can apply augmented reality, do relighting of the scene so that it's really fitting and stuff like that. But that is only applying to static scenes. And of course, much more interesting is dynamic scenes like moving persons. This is also quite some, now it's 10 years old, work on virtual avatars. How can you apply an avatar to such a model? This was a stereo mapping here. You see it's not perfect. But if you have an avatar, you can fit it to all the joints and mimic basically the motion of this person. For that, you need some good depth reconstruction. And at that time, it was quite hard to do it in real time. But then was the advent of 3D cameras. And I will just jump very shortly about this. I will actually skip this. Actual 3D cameras, you have two different principles. The one is active triangulation, where you project a pattern and then you fit it back and then you get some correspondences, all what we have seen before. And you get what is very common today now is the Kinect camera version 1. Kinect version 1 has, it's running. You can see here that is a pattern, the infrared pattern, which you don't see in the real world. And here's a depth map. And you see also here you have this occlusion patterns, the background, which is not seen from the other camera point of view. And of course, the other one, principle, which is now also implemented in the Kinect version 2 and in other time-of-flight cameras, is the modulated time of flight. So you project, you beam out light, which is modulated with some frequency, amplitude modulated. It hits the object, comes back. You can measure the phase, and that's how all these systems work that we have seen before also, which we call nowadays time-of-flight cameras. There are a complete regime of different time-of-flight cameras. This is one of the principles. And this is how it typically looks like, what we get here. This is an older type. There are newer types nowadays. This is, again, the depth image. You see, of course, it's quite noisy, so we have to do something about this. This would be the reflectance image, which gives some kind of confidence. Where could we measure and where could we not measure? For example, here you see confidence is low, the depth is bad. And this also has to be fused together. And of course, that does not deliver us any information on color. But here, what we can do is, again, like Morten also showed, we can fuse color and depth. We have a color camera. Forget this at the moment, just a normal color camera and the depth image. And then you have to do quite good calibration. If you do a good calibration, then you can map the depth into the color image. And you could do it pixel by pixel. That might lead to this gaps and artifacts. Or you do intermediate modeling like a mesh. Then you can get up to the occlusion borders which appear because of the baseline between the two cameras, you can handle here quite nice depths. And this has to be done. If you do it correctly, you can do this very nicely. You just warp the depths into the color with all the distortions, and then you have a perfect RGBD image, but only from the point of view of the color image in that case. If you go around, you might lose, because you have again a gap, like an occlusion gap. You have to handle that as well. And this can be done in real time on the GPU, and this is actually our working horse. I will show you some applications now where we use this process of first having a calibrated camera head. That can be just these two cameras. It can be a complete multi-camera head with many cameras, many depth cameras, and many color cameras. And if you fuse them all together, you can get quite some information out of the scene by mapping all this information into the color and depth map. This intermediate view is like a mesh which is distorted now because we look at it from a different field and point of view. Okay, and now this is what we call the depth compensated interpolation, and we will have a lot of applications here that we can use. We can, for example, if we have many cameras, we can interpolate between the views. We have seen this results from Fredrik, for example. But if we have depths and we handle the occlusions correctly, we can also extrapolate to some certain extent. Then you have the problem of the occlusion holes. But you can invert the problem if you say, okay, the depth is needed, like Morten showed. If you go away, you have the unknown background. But what if you, for example, put more cameras, like depth cameras from here and here, then you can do everything, interpolation and background extrapolation at the same time. I will show you some results on this. And the one example is a toy example that we made a few years ago for generating a mixed reality or virtual studio. And you know all virtual studio, normally you have your blue or green background screen, you cut out the objects, and we want to do this with depths. We've seen a nice example just now. It's exactly the same technique, and just take one depth camera, like a time-of-flight camera, and maybe one color camera, and put it on a mounted head that can sweep around. Then you can scan the room. Okay, then you have an interpretation of the room with color and depth. There you can already make 3D models, which is static. And then you continue by taking this model and adding an actor and tracking this actor with your camera head. And then you can integrate the moving actor with a pre-computed static background in 3D. And you can then add also objects, like virtual objects, and do a lot of things like lighting and stuff like that. And I have a small video that I want to show to you. Here, taking this head, for example, you can generate a panoramic image of color and depth. And then you fuse them together, then you have a 2-point whatever, not full 3D, but 2-point something representation of the scene. It is correct from the point of view of the camera. And it will not be correct if you move away, but it gives a good estimate of depth. So let me run now. I have put, it's a bit longer video, I put it into a few chunks. And I first show you how we generate our background model. And then how we put in, for example, objects and do some lighting stuff and do some interaction. Let's see if it runs.
Welcome to Mixin 3D, a flexible mixed reality approach using time-of-flight camera technology. Our goal is to mix real and virtual content, providing correct mutual occlusions, mutual shadowing, artificial reflections of real content, and interaction with virtual content. We therefore use a time-of-flight depth camera, a CCD camera, a fisheye camera as a post sensor, and a pen-tilt unit for background model construction. The background model is constructed by performing a panoramic sweep with the pen-tilt unit covering 120 by 80 degrees of the environment. While sweeping, the depth and color images are projected into two cylindrical panoramas using the angular information provided by the pan-tilt unit. From these two panoramic images, a dense 3D mesh is constructed by triangulation.
You get a good impression and you can insert objects geometrically.
In our
I skipped the tracking part. If you want to mix a very simple mixture here, you can take the background model, you take the live foreground model of the actor, and for example some virtual objects that also have depth and color, and you can fuse them consistently. So if you do this, you can do some keying, you can some interpolation, and I show you now how to plug in geometric objects into that scene. What you will see here is looking a bit crude because I deviate away from the point of view of the real camera. In the video later, you always have the view of the real camera, but here for construction you show how content is generated.
The combination of real and virtual content requires a correct alignment between the two modalities. Therefore, we use the background model as reference and place the virtual objects relative to this background with interactive pick and place. A physics engine is finally used to drop the virtual models in their final positions.
See, this is off, but it doesn't matter later because the point of view of the camera is never seen like this. It's only for geometry fitting with bullet. And, I continue. Can I run it? Oh, sorry.
A significant advantage of our approach is the possibility of interaction of real dynamic foreground objects with virtual content.
So what you can plug in is the real object, the virtual objects, and this is really interacting. It's hitting. The real object is hitting the objects. You can see this is the background.
Therefore, the geometry of background and dynamic foreground is represented as triangles and collisions are computed using a standard physics engine.
This is behind the engine.
Additionally, the shadow mapping provides a realistic perception of the whole scenery.
You can see shadows cast on the person, on the objects. This can all be done with just a very simple setup in the normal camera, computer. So this is one example how to use this as a tool. Now you all can use this if you go to Microsoft with the games of Kinect, for example. The other approach, which is nearer to what we have been doing here in form of the European projects and which will continue here, is Autostereoscopic Display content generation. And you all know how that works. I will skip through this. The important thing is that what we want to do is we want to generate content for example, here, autostereoscopic displays, where we have 9 to 70 views. And we can, this is one-dimensional horizontal parallax. You can also go to realized displays, which are at the moment, of course, static, but there is hope. This was explained yesterday. What we have here is a display which has a potential of 8 gigapixel, but only one image. But I have one video. I hope I have. It's okay if I show it to you, to the audience, where we filmed this display of 1 square meter with a normal camera, just moved around here. So this is the display. I have to shut this. And this is a display that is standing in realized premises at the time, and you can see really nice parallax. It's only this flat, but you get really very good full parallax display. It has 250,000 images. Each image is a circular image, is about also 200,000 pixels. So it's quite big, and you can see moving around, very similar to, of course, what we see with holographica, but you can go in both directions. And if you do this stereoscopically, you can also see this stereoscopically. So how can we generate all this data? I mean, this is really a challenge. And what we opted for, as was also said before, is depth-based content representation. So we take color and depth and we mix them, and then we try to generate the new data. The data for all the cameras. For example, if you have a 70 view display, it's very hard, I mean, it's very costly to place 70 cameras. So how can you do it with less? And here what we used is the format which was also presented shortly before. It's the layer depth video. And the idea behind very shortly, you have again your original camera, your foreground object, and the background object where the object is hidden. So this is what the central view sees. And if you had the right cameras, you would see on the right and the left the disoccluded areas which appear here. You can never get them from the reference image. And this would be also very hard, whereas Martin, to interpolate, because you never see in the original data that there was something hidden. So how can we estimate, not estimate it, but measure it? And we use the two-layer representation here. You can extend it to more than 2 layers, where we have the foreground layer, which is a full 2.5D model, depth and color, as seen from the central camera, which is the main camera. And then we take additional helper cameras, and we look behind the original object, and we need therefore the depth also from the side. So what we do is, here is one proposition which we had in our last European project 3D4U. This is the central camera, and then we place not color cameras only, but color and depth sets modules. This is the depth camera, this is the depth camera, and everything in between can be really interpolated, even if it's hidden in the central image. And in order to get also the colors, we have here the color camera, and so we have in this case a 5+2 setup. It has to be calibrated well, and then you can generate from this data. And the foreground data is relatively easy. What you do is you take 2 of these images. These are the 2 depth camera images here. You fuse them because you have 3D information. You can easily fuse them with 3D. So you have one consistent depth map for the foreground first. So this foreground mapping, you can see now is short video clip. You can see here that it fits, but we have really made a soft transitions in order to avoid the artifacts from looking around. So it's not very sharp, so we have to do something about this. And therefore, we use all the data. So we have our rig, and these are the 5 camera colors and the 2 depth cameras. And if you look closely here, for example, here's a person behind this second person, and if you look here, it's uncovering something, it's holding something. You can see it even better in the left camera and depth. Here the person is fully occluded, and here you can see it has multiple layers because it's holding something in front. And how can you, if you then fuse all this data, we can get all the information which is the foreground and the hidden background information. And for that we use again our working horse, this GPU-based matching. We first generate from here to here and here a mapping so that we have color and depth here and here and here and here. It will be not fully complete because there is missing information. But then we can use these data to map them to the central view, and we complete the data. I'll show you how this works. So we have here foreground and the occlusion color. You can see it's a big area that is missing in the foreground, and you still want to get it. And so what we do is we generate this 3 color depth maps which are incomplete, and then we can do again warping from the central view to the left view and from the central view to the right view, and there will be a difference which is exactly the occlusion area. In this occlusion area we can find now back in the other cameras, and we complete. So now our system has foreground layer and the background layer. So that is a full 2 layer. It's nothing extrapolated or guessed, it is measured. And I'll show you now then a small video. What would the camera baseline see? In this case here, if we take this 2-view LDV and we run it back and forth, we can see what one frame in a multi-view display would look like. In this case, it's just 9 views. And you can see that's quite nicely you can see the occluded area now in the left and right. You can see some errors because of color matching, stuff like that. Okay. This is another application, and that's the last step. How can we apply this to our new project? Okay, and think big. So we have a big system. We call it Igor. It's 2.5 meters long with 25 cameras, color cameras, and it has depth cameras. And we will exploit the same principle as I showed you just now to maybe generate a very dense light field. And I'm really looking forward to play it on the holographic display.
Okay.
Thank you.
Thank you.